Chris W. Moore, and welcome to Learning Synthesis with Pure Data, lesson number 8. In this lesson, we're going to add Midi pitch bend to our synthesizer. Basically, by the end of this lesson, our synthesizer will be able to bend up and down in pitch based on an interval that you select, and it'll sound nice and smooth and continuous. So, without any more talking, let's get patching. Okay, well, I'm here as usual, starting off with my website, lwmmusic.com. If you click on the Learning tab, that's where these lessons are located. I only have the website updated to lesson 6 right now, recording lesson 8, but 7 and 8 are going to be going up, so by the time you see this, they'll be up. And below each lesson's video, there is a link for each lesson where you can download the patches. And I wanted to show you, if you go to YouTube and search for LWM Music, so far I'm showing up at the top right here. This is because I do not have a short URL yet for my YouTube channel, but please subscribe to my channel and it'll help me get one. So anyway, this is also where you can find all the lessons here, as well as some of my music and some other PD patches. Okay, so let's get to the lesson. Okay, so here is our patch thus far. I'm going to zoom in on it. It's the lesson 8 folder if you download it. All the file names are the same as the previous lessons. Oh yeah. I have not, what do you call it? I have not added any modules in these last 2 lessons. But we've been refining the synthesizer. So let's look at it here, and actually let's hear it. So it's a smooth monophonic synth, and now it has pitch bend. And you can even set your pitch bend to whatever interval you want it to be, like a perfect fifth. You can bend up and down a perfect fifth. Alright, and if you want to do up, I have it set to go up to 2 octaves worth of bending up and down. Something more than that might be a little bit too much. But in any case, let me show you how we did this. And yeah, so I'm going to right click on this module and open it. This is the MIDI in module. Basically, I added one number box here. It's the amount number box. That's where you can say what the amount of the bend is. It's the same amount up and down. And this is the pitch bend readout. If you don't have pitch bend on your keyboard, you can use this, for example. But, you know, getting back to exact 0 is a bit of a challenge. So anyway, you probably have pitch bend on your keyboard. Even the tiny little nano ones have it to some degree. So anyway, what I needed to add in this patch, this module, to make this all work is, since we have note, velocity, pitch bend, amount, and mod wheel going out, we have not applied the mod wheel to anything yet, but that's coming up soon. Basically, I need to make sure there was 5 messages going out, so that's why there's 5 floats here in the pack object. And I have a trigger bang float for each one of these. Once again, the importance of this is, since this is all a packed message, anytime there is a value going into any of the inlets except for the leftmost one, it doesn't necessarily send it all out. So if you bent your pitch bend wheel, you wouldn't hear anything until you played a new note, or you wouldn't hear a difference. And you can't have that, so that's why these trigger bang floats, basically the bangs are hooked up to the leftmost inlet, So that way, as these numbers change, they automatically bang here and send the whole message out. So anyway, that's all that needed to be changed in the first MIDI module. In the oscillator section, there's also a change. Once again, need to make sure there's 5 messages coming in. I have these little subpatches here called PDV. Those are valves, and I'm going to explain those momentarily. Just remember, as I stated before, since we have trigger bang floats banging each time, like pitch bend or any of these values change, the whole stream of information comes through. So basically, every time you move the pitch bend wheel, note, velocity, and mod, they all go flying along with it, as well as pitch bend amount. So I have these valves on so that if, yeah, I guess I'm explaining them right now, aren't I? Okay, let's go. So that as these values change, let me open the sub patch here. Basically, I have a little bit of protection here. See, a number comes in, it goes into select, its creation argument is -1. I chose that because nothing's basically going to be a -1 value right from the start. You know, none of the MIDI controllers, notes, velocity, any of the MIDI information starts off -1. So that way, this thing is basically open as it happens. Basically, whatever number's in the right inlet, that number gets blocked, and it starts off as -1. So unless a -1 comes through, the right outlet here from select is going to flow. And what it does is it goes into the float box. Now, it goes by way of this trigger float bang. So really, the number coming out of here goes out the left inlet here and gets stored in the float box. And as it does, it bangs as delay 10. And delay 10, after 10 milliseconds, which is a really quick amount of time, bangs the float box. And what it happens when it does that is it basically bangs the number out to continue, and it bangs it into the right inlet of select, which now means if that number comes again, it'll come into select and send a bang out the left inlet, which is not hooked up, thereby blocking it. It doesn't flow through the right outlet unless it's a different number than what was just sent into the right inlet. That way, numbers only flow through and come out the outlet here if they're new numbers. If it's the same number that's already been sent, it doesn't send it again. The main reason is you don't need the frequency being sent again. If it's the same frequency, the oscillator is already at it. You see it's still oscillating at the frequency I last played. And we don't hear it because the envelope shuts it off when you release a note. But the oscillator is always going. So we don't need its frequency to be sent again. It just creates clutter. And then the same thing here with pitch bend and amount. So, like, let's say you're holding the pitch bend wheel up and then you play a new note. I don't know why you would, but let's say you did. And that new note, the note will come through, but the pitch bend value won't come through again because it's the same if you're holding it steady. And so it doesn't, I mean, the whole idea is to not have all these numbers flowing through unnecessarily. And we'll see later why that's also important to make it a smooth pitch bend. Okay, now in this sub patch here where we have all the oscillators, basically I made some minor changes here. First of all, each of the sub patches here for the oscillators, you'll see its inlet has now been labeled freak, short for frequency, because frequency values are coming in now instead of note numbers. Because everything's going through this sub patch here, where basically note, pitch bend, and pitch bend amount get calculated, and whatever resulting frequency comes of that then goes into these oscillators where it's sounded, if the oscillator's on, depending on which waveform you have selected. See prior lessons if you don't know what I mean by that. But in any case, it used to have an M to F here, so we don't need that anymore because it's already been converted to frequency. And just for security's sake, I have a PAC F50 here and a line tilde, converting it to an audio signal so that if somehow there's some jumps between numbers that happen quickly, this smooths them out on the way in. We've used that for amplitude control to remove artifacts and stuff. It's good in digital to have little ramps like that if you can on some things so that things sound smooth. If you hear little snaps, artifacts, then it's a sign you need to put one of those in. And you see we have them here for turning on and off the oscillators as you select different waveforms. We've set all that up before in previous lessons, so you may want to check those out if you're just seeing this for the first time. Now here, this is the meat of it. This is your frequency generator that takes a note, pitch bend and pitch bend amount, and comes out with the appropriate frequency. So we have an inlet here for the note, comes in, and then we have here minus 12 is what it says. That's the creation argument, but this changes as you change the amount. See, now that it's set to 24 as I just did, these right inlets basically, you don't see the new number display, but it's now set at 24. So basically you get the note as it's labeled here. The same note is in the center. The note minus whatever number in MIDI note numbers or semitones here is subtracted from it. You get that as your bottom range, and then this is your top range. So basically whatever your amount is set to, it will immediately calculate each time you play a new note what the minimum and maximum range is going to be, whether you're bending the pitch wheel down or up, and what the center unchanged frequency would be. And speaking of frequency, right here is where we have M to F objects that convert the MIDI notes to frequency. So here's where I, based on interval math, am able to say what the MIDI note numbers are for the upper and lower range of the bend range, and here they get converted to frequency. It's just easier to do it math-wise here first, and then here now we're in frequency numbers in hertz, and I have 3 number boxes here for each of these. I used the longer number 2 boxes here. I may not have had to, but I did that because it has a wider range of number values that it allows through, and so I just wanted that higher resolution just in case, although I don't think it was absolutely necessary. But in any case, I'm not changing it back. So here's the lower range. It goes through here. Basically what gets calculated here is we take whatever the lower range is and we subtract from it what the unbent note is. That's what this TBF is for in this minus sign. Here we take whatever the lower range is in frequency and subtract from it the frequency of the middle note, and what you get is a negative value. I want that because it helps out with the math later. Otherwise, if I would have subtracted the pitch in frequency, subtracting its lower range, then you get the distance in frequency in hertz of the distance between the unbent note and the lower bent note. That's what I'm trying to get, but by subtracting the other one from the other in reverse, basically I get it in negative values. And I want that. It makes the math smoother later. Over here, we're doing the same thing, except in this case we're subtracting the unbent frequency from the bent up frequency. So what these are the maximum range in hertz of how far you would bend up if you move the pitch bend all the way up, and how far you would bend down if you moved it all the way down. And in the center is your unbent frequency. These are distances now. This is not the frequency of the note that gets played, but these are the frequency values or the hertz values for the distance that it would be changed if you bend them all the way. Now here is where we have next these multiplication sections. In case you're wondering why there's TBFs here and here, it's the same as before in the packed message from Midi. Basically, the right inlets of your math objects don't necessarily do the math. They'll store the number, like here the minus sign as well as the multiplication sign. They'll store a number that comes in the right inlet, but it doesn't do the math unless the number comes through the left inlet or a bang is sent. Both inlets store numbers, and whatever the last number is, they're in there. But with the right inlet, you need to send a bang to say, okay, do the math now. So this way, the TBF for the right inlet value basically says no matter which number changes, whether it's this one or this one coming in, it's going to do the math. And I want that, so that's why there's TBFs all over the place. There are trigger bang floats. It triggers a bang and a float at the same time. So these multiplication signs, what I'm doing now is I'm basically scaling these numbers. This is the distance in hertz. I'm scaling them by a percentage. Basically, over here, this is the section where the pitch bend wheel values come into play. How far are you bending it down? How far are you bending it up? All that gets converted to percentages here and then gets multiplied by the distance here. So this will determine how far up it's bent by multiplying this number and distance by the percentage. Over here, let's look at this because we got to see it. This is where the pitch bend values come in, and the pitch bend wheel, when it's bent all the way up, is 16,383. When it's in the middle position, and many of them are spring loaded so that it snaps back to the middle position, meaning no bend when you let it go, and that value is 8,192. Its lowest value is 0. So 0 to 16,383, that's 16,384 different values, a 14-bit number, 14-bit resolution. That's what gives you all these incremented numbers in between that allow you for a smooth pitch bend. The middle number is 8,192. Since 16,384 is an even number, there's no middle value because it's an even number. So 8,192 is the official middle, and that means you have less numbers above than below. That's why I divide it in half here. Basically, whatever number's coming through, I subtract 8,192 from it. So that way, if it's 8,192, it becomes 0 here, meaning no bend. And then we go to Moses. And just like the Red Sea, this Moses parts things based on whatever number is put here or fed to it. I just have the creation argument of 0, so that way it doesn't get changed. Basically, 0 and anything above it comes out the right, and anything below 0 comes out the left. And so when it comes out the left, that means it's below 0, and I do several things. We're going to ignore these two messages here and just go with this one. This is the float number, the number itself. It goes down here, and it gets divided by 8,192. Because the lower range, once we've subtracted 8,192 from 16,384 up here, we get a range of 0 down to negative 8,192. So if you divide it by 8,192, what you get is a percentage down here in negative numbers because of you're dividing it by a negative number. And since all these would be negative on the left side coming out of Moses, then we end up with negative here, which is why I want negative over here. Because then when they get multiplied here, the resulting percentage becomes a positive number now, because two negatives multiplied by one another becomes positive. And so that's why this is here. This is a percentage here, multiply it by the distance range, and basically however much you're bending it down, it calculates the hertz in proportion to how much you're bending it down. Now over here on the right side, once again, we're going to skip the two messages here and talk about them later. The float comes through and it first hits a select object. When it goes into select, its creation argument is 0, meaning if it's a 0, it's going to bang out its left outlet. If it's not a 0, well, something would come out the right outlet, but I don't use that. Basically, I just want a detector to say, okay, 0 came through. If 0 came through, it sends a negative 0 in the message box here to the percentage on the left side. Also, if a 0 comes through, it still goes straight through here, too. As you see, I have a negative 0 now and a 0. That's because the pitch bend is not being moved. And so on both sides, I have zeros. This one's negative because remember right here, it becomes positive when you multiply it by another negative. So that's why I need a negative 0 here. Here, we just take the 0 and everything above it, and it's positive. The reason why I want 0 to be a possibility on both sides is depending on whether we're bending down or we're bending up, I want it to come through once you hit 0. I was having trouble when I was making this that if I just had it come through one side only, like if I was coming through the right side or the positive values and 0 was only a possibility over here, then when you were bending down and you come back up, it would actually sound a little bit down from the actual central pitch, and on this side, the opposite. So this way, if it goes to 0 on both sides, zeros will definitely come through when you get to 0. Now back to these messages here. These ones and zeros get banged through whenever, for example, if things are flowing through the right side, these bangs will send this bang will send a 1 here to open a spigot I got at the bottom for the right side, and a 0 here to close the spigot for the left side. So basically, I don't want both sides flowing at the same time, so that when you're bending upwards, the negative number stream is shut off. And then when you're bending downwards, the positive number stream is shut off. So that somehow if something comes through, I was having a little trouble with that earlier, basically it gets shut off. I mean, so that way eventually you want the resulting frequencies to come out, but you only want them to come out depending on which side you're actually on. Even though they shouldn't, I was having little glitch problems with it, and so this was just an extra protection to make sure, when things are flowing through the left side and these numbers are changing, it shuts off the right side and turns on the left. And the exact opposite over here, it shuts off the left and turns on the right. Okay, now we got as far as the percentage, as far as the math is concerned. So here you get a resulting percentage of the distance up and down. That basically calculates how far up or how far down you're bending the pitch. And it can be 0 on either side at this point. Then next, in order for the resulting frequency that comes out to be the frequency of the note or the pitch you're actually playing, I have the central original note that whenever you play a note, that note stays the same here coming out of this central line. And what happens is that note subtracts from it the distance in hertz you're bending down. And then the result is basically the actual frequency you bent down to. And the same thing on this side, except it's addition. How much of a distance in hertz are you bending upwards is coming out here, and it gets added to the center frequency of not bending at all, and so it determines how much or what value in hertz is the frequency that you're currently at. So then here's the spigots that shut off one side or the other. And then that all goes through this $150. This is almost like the pack F50s that I made before. In fact, I don't think I really need these. I was just putting them on before because I was having increment problems. Like numbers were shall we say, I was bending the wheel and it was going to different degrees of frequency, and kind of like it sounded almost like a microtonal scale rather than a smooth bend. And so I was trying to smooth things out. And actually, yeah, I am going to get rid of them. They are unnecessary now. There's probably some other things that are unnecessary, but I'm just going to get rid of those because they just look crappy having them there. And since there's no line message right afterwards, they're not doing anything, believe it or not. So I got rid of them. Goodbye. It was working. But anyway, it goes out the outlet here, and that is the outlet at the bottom of the sub patch that I have feeding all of the oscillators, depending on which one you have selected, whichever one's turned on. All the others are turned off at the same time. So basically you get a nice resolution there. Of course, you hear a little more degree of bend the smaller your range is that you're bending. So for example, let me close these guys up. We're done with this module. If I go here to my amount, let's make it 1. So now it's bending a half step, minor second basically, depending on what notes you're playing and what key you're in. But it's a half step, semitone. And so basically, when you have a shorter distance as your maximum range, you hear more divisions of that distance and a more gradual bend. You just can't really help it as you make your interval of bending larger. That 8,191 values up and that 8,192 values down divide up less and less of a slope and frequency. Or wait a minute, more and more of a slope and frequency as your intervallic distance is larger, and thus it sounds like bigger jumps as you bend it. One last thing I had to change also, let me show you here. The ADSR module, first of all, had to expand it to 5 floats coming through. Even though this one only receives velocity to start and end notes, I put a valve on it, and that was necessary because this guy, here I'll show you. This was the source of a lot of frustration earlier. I'm going to take out the valve temporarily. Don't move that. Just connect the second value here. The second float in the packed message is velocity. Connect it up to the inlet here. If you remember, our ADSR had this feature that whenever velocity is coming through and it's a non-zero value, it was hitting this 0-10 thing to shut off the release over here. And what that did, when you move the pitch bend wheel, since, as you saw earlier in the Midi module, since values are coming through, even if they're remaining the same, like as I move the pitch bend wheel, note, velocity, everything else still flows through because it's being banged out by the trigger bang floats. So and I was hearing that thing, and that's where I was putting on all these packs and lines and stuff trying to get rid of that. And then I figured out what it really was. I still want this here so you could cut notes really short and play fast and hear a little separation between the notes, because you need it to be closing off this guy in case you have a new note come and you want to stop this release and have the new note start. So I have that there, and I wanted to keep it. But then I realized what the problem was, and I put valves on everything because really in the future, as we add more things, we're really going to want that. Basically, by having this valve here, the velocity, which is not changing, like I'm holding down the key. The velocity staying the same until I release it. Oh, I think that went to the wrong inlet there. The the velocity wouldn't change until a zero comes, like when you release the note. So the same velocity was getting sent through like a new note's being played, and it was triggering that thing, which was making things stutter. But by putting that little valve on, everything's smooth. Of course, I'm just bending one semitone, which is not much. Let's make it a perfect fifth again. That doesn't sound right. Hold on here. 7, right? There we go. I guess the thing was the amount didn't change until I played a new note. That was probably what was going on there. Let me just make sure. Let's quick change this to minor sixth. Yep, okay. Derp. You gotta click it right. 13. Enter it and hit. You gotta hit enter after you type in a new number. There we go. Okay, good. Yeah, it's working. It's fine. It's fine and dandy. Default, when it loads up, it's set at 12 for an octave up and down. Okay, so that is this tutorial. If you download the lesson 8 patches, you get this. Also, remember, these little lines from the patch cables, we'll get rid of those in the future after we're done with all our modules. They disappear as you open up modules. For example, I open that, close it, now the patch cable's not showing anymore. But when you open the modules patch, which has all these subpatches in it, you see the patch cables appear on top of it, and that'll disappear later when we clean it up. But after we add all our modules, then we can frame it all and make everything look nice and sparkling. Okay, that's it for this lesson, and if you like this video, please like it on YouTube, and if you have a question, please drop a comment in the comment box. And need subscribers, so if you want to hear more tutorials, please do subscribe. Alright, take care. Alright, so now that we reached the end of this lesson, Crafty has another thing he wants to tell you. Yes, Crafty says he wishes he could subscribe to the channel, but he can't because his paws won't work a keyboard or a mouse. So you'll have to do it for him.